Hello. So this is the first in our online video lecture series for ECE 695, and I'm going to start off today with a tutorial on GPGPU-Sim, which is an architectural simulator that you could use in your project to model that models a real GPU that you could use to evaluate different architectural techniques. So what does this thing model? It basically models everything we've gone over in class and more. We focused a lot in class on the SIMT Core itself, what's going on inside, what the pipeline looks like, how registers are read, etc. And it models that in addition to the whole rest of the memory system. So there is a model for the interconnect that allows you to create different types of interconnect configurations. There's a model for each of these memory partitions with memory controllers that allow you to control the memory access schedule. And then there's a model for the DRAM itself that includes timing parameters for pre-charging, activating lines, row buffer hits, etc. So if you wanted to model something in that level of detail in the memory system, that's also possible. So what do you need to run this? It is a C++ simulator, so this is not RTL, this is not Verilog. It's all written in C++ to be precise. It runs on Linux. You need CUDA installed, a bunch of standard Linux setup stuff like GCC and Make. And one thing you should know is that you don't actually need a real GPU to run this. So you can run it on your laptop, you can run it on some desktop that you have, and you can run it on clusters that don't have any GPUs, like qstruct, for example. So you don't have to log into Scalar to run GPGPU-Sim. You can run it on qstruct or any other Linux distro that you have. Now, the code that I'm going to point you guys at is a code base that my research group actually maintains, which is going to be integrated into the latest version of the simulator. I'm pointing you at this code base because it is the most up-to-date and the most rigorously validated of all the versions of GPGPU-Sim you're going to see out there. So what do you need? GPGPU-Sim runs with a bunch of different toolkits. We're going to focus on 9.1 because that's the one that we do the most work on validating. And there are a variety of dependencies that you need just to make the simulator work. They're listed here. If you want to do detailed plotting, there's a plotting tool called Aerial Vision that you can use to get nice, time series plots of, what happens to your L1 cache accesses or hits or whatever over time. And so you can look at, in these 1,000 cycles, we had this many hits. In these next 1,000 cycles, we had this many. And you get nice time series plots. And all of this is done for you without you having to write any code yourself. And that's through this Aerial Vision tool. You don't necessarily have to use it, but it's really great for gaining insight into what's going on inside the machine when you run your programs. And there's some other dependencies for documentation that you may want to take a look at. If you just have a fresh Ubuntu install and you want to run GPGPU-Sim, this single command line will basically get you all the packages you need to get the thing up and running. I'm going to provide a brief tutorial on how to get this to work on qstruct. So qstruct is the ECN infrastructure that many of you may have used in 565 for running Gem 5. You can also run GPGPU-Sim on qstruct. qstruct doesn't have CUDA installed, so these are some straightforward instructions, series of command lines that you can run to get CUDA installed on qstruct. I'm not going to go through them because it actually takes a couple minutes to download and install the thing because it's several megabytes. And after you've done this, you will have CUDA installed on qstruct. And again, you don't need a GPU to run GPGPU-Sim, so once CUDA is up and running, you should be able to run the simulator. The GPGPU-Sim code itself is located on this GitHub repo, and these are the commands that you should run to get the code. You should run the dev version of the code. Okay, so you're going to clone it, you're going to move to the directory, and then check out the dev version. Make sure that CUDA install path is set up. So I told you guys to set it up right here. If you're doing it on qstruct and you follow these instructions, then that's fine. If not, just make sure it's set up if you're running it on your local machine. And the first thing you have to do is actually source this setup environment script, which will set up all the various environment variables that GPGPU-Sim needs to work, and then you should just be able to run it. So I'll give you just a brief, so you believe that this really does work. Okay, we can just do this on qstruct very quickly to show you what you'll need to do. So at this point, I've already installed CUDA. Okay, so I'm just going to go and I'm going to put GPGPU-Sim on qstruct. I guess I already had it on here. I'll just get rid of it. And then show you guys what you need to do. So you basically just clone the code. You move to the directory. And then I want you to check out the dev version. Okay, so you should be able to see what's going on here. So we're sort of on a clean tree, and we know that we've got the, oh no, I don't actually have that set up. Okay, so you want to make sure you have your CUDA install path set up. So for me, on this machine, it's going to be under CUDA, and then I will go back to these instructions. Okay, so we're going to source setup environment release. Now, the reason why we say release here is because you can actually set up a debug build for GPGPU-Sim. So you'll get this whole print that says that the setup environment succeeded. If you wanted to compile the simulator in debug mode, meaning that you coded something up and you don't know why it's dying, you don't really want the binaries compiled with full optimization, what you do is you basically source setup environment debug, and now when you type make, it will actually make the debug version of the simulator, which is very useful if you're trying to actually debug a problem that you have. For now, we're just going to essentially just make GPGPU-Sim in the release mode because it runs probably 20 times faster than the debug version. And so it'll compile a variety of warnings in the source code. You can safely ignore those for now. And so we'll sort of leave that go. It doesn't take that long to compile. It's not Gem5. It probably takes only a couple minutes on qstruct to actually get done. Now, after it's compiled, you'll want to run a benchmark. And so the way that GPGPU-Sim works is that you compile an executable with CUDA the same way you would when you run it on a real GPU. But when you source that setup environment file, it actually played with some of the paths in your environment. And so instead of trying to run the executable on the GPU, like the real machine that would happen if you didn't have GPGPU-Sim installed, it will essentially trick the executable into thinking that the simulator is the real GPU. And it will start running all of your CUDA commands on the simulator, and then you'll be able to actually execute the program that way. So to run a benchmark, you really just have to have a benchmark compiled with CUDA, make sure it's the same CUDA version that you compiled the simulator with, and then if you source this setup environment in GPGPU-Sim and then run the benchmark, it will run with the simulator instead of the real machine. Okay, and so GPU benchmarks, you already have one that you made in assignment 1, so you could actually run that in the simulator and it should work. With the big inputs, it's going to take forever because simulators are several orders of magnitude slower than real machines. So, there's a couple things you have to do. You have to make sure that the configuration file and the interconnect file and the McPath file, if you're looking at the power model in the simulator, are all copied to the directory you're running the program from. There's actually a collection of benchmarks that we maintain that are sort of ready to go. And if you follow these sets of instructions, you'll be able to just run them without any messing around with setting up the benchmarks, etc. I'm not going to go through all of these commands right now, but there's a whole variety of benchmarks inside this Git repository that you can use to evaluate your particular architectural component on. And these instructions will give you a very detailed step-by-step on one particular benchmark suite, which is a fast-running version of Rodinia that you can use to just make sure that everything is up and running. And we'll come back to this later, but I'm not going to go through the details of doing all this now. But if you follow these instructions on slides 10 and 11, you should get basically a collection of 12 benchmarks that you could just run without any additional work. Okay, so let me go back into the setup of the simulator. So some of this is a review of what's going on in CUDA, which you guys already know about. Okay, that basically, there's this big grid of threads that are launched, and the grid is further subdivided into thread blocks. And then when it actually runs, they run on these things called warps, which are groups of 32 threads. You already know all of this stuff. How does a warp work? We covered this in class. There's a common PC, and all of the scalar threads will execute the same instruction. If they're not on the same control flow path, then they're basically masked off. All right, so we're going to start out with the SIMT core. And again, this is what the simulator models, and it is almost exactly what we've detailed in class for how a SIMT core is built. So, this is the general overview, just a repeat of what we've done from the microarchitecture section of the class. This is what the core looks like. All three of these schedulers that we talked about in class, the fetch scheduler, the issue scheduler, and the operand schedule are all modeled inside this simulator. Fetch and decode are modeled exactly in the way that we've talked about, where you essentially fetch from one or n different warps in each cycle. There's an iCache modeled, and this iBuffer is also modeled inside the simulator. And again, we'll walk through the code once we get through the basic setup of what is involved, what is actually inside the simulator. Instruction issue is again the same way that we studied in class. You will fetch instructions that will be stored in the iBuffer. The issue arbiter, there are actually a number of pre-coded issue arbiters that you can use inside the simulator. By default, the configuration that you'll use, which is a modern Titan B configuration, which is the most up-to-date one, we'll use a greedy then oldest scheduler, meaning it will just pick from the warp that issued last until it cannot issue anymore, and then it will go back to the oldest warp and attempt to issue from that warp. When an instruction is issued, there is code inside the simulator that will do the following. First, it will do the functional execution of the instruction. So one thing you should know about the simulator is that the functional model, meaning what result the instruction actually produced. So if you have an add and you add together two registers, and then there's some output to a third register, that output, that actual result, is completely separated from the timing model. So as soon as the instruction is issued, we functionally execute it. So even though it's not proceeded to the writeback stage, since everything in a warp is issued in order, it's safe for us to functionally execute that instruction as soon as it passes the issue stage. So we know what the result of the instruction is before it gets to writeback, which is fine in terms of simulation, and it actually allows you to do some interesting predictive stuff if you wanted to do some, Oracle-based things, because you know what the result is before it even goes through the execution pipeline. And so the simulator is decoupled, meaning that there is a there is a functional simulator and there is the timing simulator, and you could actually run the functional simulator as a standalone without any of the timing. So by timing, I mean trying to figure out how many cycles does this program take to run. And so when we do the issue, we first sort of tell the functional simulator we want to execute this machine instruction. We get the result back, and then we can use that result inside the timing model, whatever we want. If it's a memory access, we will figure out how coalesced it is and figure out how many accesses this instruction will generate. And so we need to know what addresses every thread is accessing, and then we figure out from that how many memory accesses end up being generated. And at issue, you also reserve the output register in the scoreboard. Okay, so the basic scoreboard we studied in class, the in-order scoreboard is used here in the simulator. And when you do the issue, you basically take that output register out, so that way no other instruction can come in and clobber that output register before we've actually written it back. And if it's a branch instruction, then we have to update the SIMT stack. If it's not an instruction that affects control flow, then there's nothing to do here except simply move the program counter for the top of the stack forward. If it is a branch instruction, then we have to figure out, well, which threads are going to go which way. And we do all of that when we issue the instruction. So after issue, you sort of know what the result of the instruction is, what the result of all the branches are, and then it will flow through the timing model to figure out what is, how long this instruction actually takes. The scoreboard is essentially exactly the same as has been described in class. It checks for dependencies to make sure that you don't violate raw, or you don't have any raw or read after write or write after write, dependencies or hazards. The instructions are going to be reserved when the registers, you're going to reserve the registers when the instructions are issued, and then obviously they get released when the thing is written back, just like we studied in class. SIMT Stack, you guys know how this works. This is handled inside the simulator, and there literally is code that performs this stack-based operation on branches to try and figure out how things diverge and reconverge. So all of this is also modeled inside the simulator. Operand Collector, also modeled inside the simulator. So there is code that essentially models this picture that you can use to modify in whatever way you like. Pipelines, so all of the basic pipelines are there. The SIMD execution unit, they are pipelines. So on every cycle, the instructions may take, for example, 20 cycles to go through the floating point pipeline, and that is modeled in the simulator. And so on each cycle, you will be able to issue a new instruction into the pipeline, depending on how it's set up. But it will take several cycles for the instruction to actually complete. And these numbers have been validated against a real machine when we tried to figure out what the pipeline depth is for each type of instruction in each pipe. The bandwidth and latency here is configurable. Okay, so there is some configuration options inside the GPGPU-Sim config file, which we'll talk about once we start looking at the software architecture, that you can use to tweak those two variables. By default, we basically have, for ALU pipelines, a single precision, a double precision, and what's called SFU, or special function unit pipelines, to simulate ALU instructions, ALU-like instructions. Writeback is obviously what every instruction goes through in the very last step. Each pipeline actually has its own results bus with a couple exceptions. Own results bus, meaning that you're not going to contend for the bus on writeback between competing pipelines. The exception is the single precision and SFU pipeline. They share the same results bus. And the slots here are pre-allocated. So we know who's going to use the results bus at what particular time. And there's code inside the simulator that prevents prevents them from both trying to use the results bus at the same time. Probably the most interesting part is of the SM and of the entire simulator, or at least the most detailed part is what goes on inside memory. So inside the core, we model all the different types of memory that exist in the GPU. And so this little diagram here basically shows all the different types of caches that exist inside the SM model. The data cache is what is used for global and local accesses from the program. The shared memory is the scratchpad memory that you guys hopefully all know a lot about from doing your assignment number 1. There's also a small cache for constant accesses, and then this thing called the texture cache, which we haven't really looked at too much, but we'll talk about that a little bit more in a successive lecture when we talk more about the memory system. In the front of this is this thing called the AGU, which conceptually is what's known as the address generation unit. This is the thing that spits out all the addresses for all the threads that you want to execute on from an instruction on any given cycle. There's code inside the simulator that will do the coalescing, like we said, and after the coalescing, you will access the cache based on whatever the number of accesses generated from all the threads are for global and local memory accesses. There's code inside the simulator that will also figure out what your bank conflicts are in your shared memory. So we talked about bank conflicts in class. That is modeled inside the simulator. So if you have a bunch of accesses going to the same memory bank, it will essentially serialize those accesses, and it will take longer for those instructions to clear the memory stage of the pipeline. Quick notes on constant cache. And this usually doesn't matter all that much, but it is modeled inside the simulator. It's a small read-only cache for constants. Right now, there's only a single read port on this constant cache. If you access more than one location, then you're going to end up being serialized and can cause stalls. Typically, you usually hit almost all the time in this cache on the stuff that is constants. If you want to increase the number of ports here, it is configurable from the config file. Texture cache, again, don't worry too much about this. It's probably not relevant for a lot of the workloads that you may want to look at. It was important in the early days of GPUs because there was no L1 data cache. So if you wanted to actually cache data in the SM without using the scratchpad in CUDA, you would have to declare your data structures as textures and load them through this texture cache. Today, people don't really use the texture cache, but it is still modeled, and there are still texture instructions in modern GPUs because obviously graphics need textures to render images. If you don't know what a texture is, it's not a big deal. We will again cover that a little bit more later in the class. Essentially, it's a special type of cache that's modeled here that exploits an access pattern that is very common when you're shading or trying to figure out what the colors are for pixels on a screen. So I'm not going to belabor this too much. We will talk a little bit more about the texture cache and how it's modeled when we discuss the memory system in a bit more detail later in the class. So the shared memory unit is modeled in the simulator, as I mentioned earlier. This is the scratchpad. You guys use this in your programming assignment, hopefully. It is modeled to be a single cycle read, so essentially as fast as a register file if you don't have any bank conflicts in the shared memory. And those bank conflicts are modeled inside the simulator. Like we discussed in class, this shared memory is dynamically allocated between the different thread blocks when the thread blocks get scheduled onto each SM core. So this is the same sort of thing that we talked about before regarding bank conflicts here. These are modeled. You can configure the number of banks. By default, most of the modern GPUs have 32 banks, and that's what's modeled by default in the simulator. If you have more than one access to the same bank in the same cycle, it serializes the access, and that instruction gets stalled in the memory unit for extra cycles. This is just pictorially what's happening with bank conflicts. This is a repeat of what we said before. If you're accessing different memory locations in the same bank, it's going to serialize. If you're accessing the same memory location in the same bank, it's going to broadcast that back. But if it's a different memory location, then it can only read out one per cycle. And in this case, we have no bank conflicts, right? Because every thread is going to a different bank. And in this case, we do have bank conflicts because different threads are going to the same bank for a different location. Global memory is probably the most interesting memory system in the simulator. And this is the biggest, slowest memory that's available. So when you buy a GPU and it says that it has 32 gigabytes of memory, this is global memory. In order to access this, you have to go through the interconnect. It's off chip. So what happens is you have the core, you have your interconnect. These are all on chip. You take the request from the core and it goes through the interconnect to the memory controller or memory partition, as we're calling it here in these slides. And then the memory partition will figure out how to access the off-chip DRAM. And there'll be multiple channels, and all of those channels are modeled in the simulator as well. So you go through the interconnect, you go through the memory partition, and then you go all the way to the off-chip DRAM. You can cache this. So modern GPUs, there is an L1 data cache and an L2 unified cache. There's also an L1 instruction cache that's modeled in the simulator. I didn't talk about that much because the hit rate there is usually very, very high. But the L1 data cache, you can turn it on or off in the simulator if you want. Modern GPUs do keep this on, so the default configuration for the Volta machine that you have access to will have the data cache on. And the L2 is a memory side L2, meaning that it's shared, so it's not private. So all of the L1s are private per SM, and the L2 is a shared L2 across all the SMs. So there is no coherence problem at the L2 because there will only be one unique place that a cache line can live in the L2. And it's unified because it stores both instructions and global data and texture data and what have you. Global memory is coalesced. So we've talked about this in class. This is just basically saying that you have 32 threads in a warp. They may all access the same contiguous cache line or 128 byte worth of memory. If that's true, then we'll just generate one 128 byte request to either the cache or the DRAM, instead of doing a bunch of 4 byte transactions, even if the cache is turned off. So there are two situations here. One is that the L1 cache is turned on, then the granularity at which you access the memory system is in cache lines. And the other is that the L1 cache is turned off, which means that you don't access things in cache lines, so you have to access memory at some level. And the way that it works in the simulator is if the cache is turned off, you will coalesce things down into 32 byte requests of the memory system instead of 128 byte requests. I will mention that the modern Volta card that is modeled in the simulator today, in the code that I've pointed you at, is a sectored cache. It has 128 byte cache lines, and there are 32 byte sectors. And when you miss in the cache, meaning the tag for that particular cache line is not there, you will go and collect 32 bytes if that's all you need. If you need the full 128 bytes, then it will go fetch those full 128. The whole point of the coalescing is to basically reduce memory transactions. So even if you hit in the cache, the number of transactions you create in memory is important. And so if you coalesce, you basically have less accesses to the L1, you need less L1 throughput, et cetera, less traffic on the memory interconnect to memory partitions, et cetera. This is a very simple example of coalescing. So you have the threads in a warp. This is different regions in memory that those threads are accessing. If they're all accessing the same 128 byte contiguous chunk that is aligned to 128 bytes in the memory space, then you'll generate one transaction. If you're spanning more than one 128 byte chunk, which in this case is just because of an alignment issue, you'll have to generate two 128 byte transactions. How is the L1 data cache configured? So the L1 data cache is used for both local and global memory. So we talked a little bit about local memory earlier in the class. The difference between local and global is that local memory is memory that we know is private to a particular thread. So some examples of local memory would be when you spill and fill registers, when you're doing function calls, etc. The stack. So if you have variables allocated on the stack, those are local. So there are special memory instructions and a special region of the address space that is devoted to these local accesses. So we treat those differently than we do the global memory accesses because we know that the local accesses are going to be thread private. So the policies on the L1 cache are different for the local and global memory. For local memory, it's a write-back cache, so you can have dirty data in your L1, but it's not really an issue because no other thread will read or write that data because we know that it's private. Global memory, on the other hand, is write evict, meaning that when you do a store instruction to the L1, it will evict it from the L1 cache, and it will write it back up to the L2. Both of the local memory and global memory are write no allocate policy, meaning that when you do a store and you have a miss, you will not allocate that line in the cache. So essentially, store misses will go around the L1 data cache. And then store hits obviously are different for local and global. That's what the write hit is. One thing that we've talked about before is that in NVIDIA GPUs using CUDA, these caches are non-coherent, so you cannot expect the threads in different SMs to see the same update order like you can in a traditional coherent multi-core CPU setup. Maintaining coherence is very expensive on GPUs, and the programming model sort of encourages you to not rely on global memory accesses being coherent. There are ways to try and make the cache coherent and maintain some type of memory consistency, but by default, there is no coherence and there is a very loose sense of consistency between memory accesses. The cache that's modeled in GPGPU-Sim is a single port cache, meaning that you can service one 128-byte word in one cycle, and this is something that can be configured. If you have an access that has multiple, or an instruction that generates multiple memory accesses, so it's not coalesced, then it will take several cycles to clear the instruction because you'll have to probe the cache with the first access, second access, etc. When you miss in the cache, we have to track what's going on. If you're caching the accesses, we use miss status holding registers, which we talked about earlier in the class. And it's not just one miss status holding register, it's many. Because in GPU caches, you want to be able to miss a lot to saturate the memory bandwidth of the machine. So there is a huge array of miss status holding registers, which is what's implemented in the simulator. If you're not caching the access, then you don't really have any MSHR. So what the simulator does is encode the warp, the target register in the packet that we send out. So essentially, you have a miss, you need to fill a particular register for a particular warp. That information will get encoded in the request that gets sent out over the memory system. When it goes to the memory unit and it finally gets the data back, when it replies, it knows what warp, what target register this should be filled in, fills the register, and then frees it from the scoreboard. MSHRs, this is just a brief overview of what MSHRs are, if you forget, but basically they are ways to merge memory requests to the same location in memory, so that if you miss on one particular cache line in one particular instruction, and then another instruction comes in and misses on that same cache line, you won't generate a redundant request. You will just take a look in the MSHR, see if you've already missed on this particular access. If you have, then when that access comes back, you will fill in the data for both the first instruction that generated the miss and the second instruction that wanted to access the same cache line after the first one came through. This is what's implemented in the simulator. We don't know exactly what's going on inside the hardware. The intimate details of what's going on inside the cache are not necessarily public. There is some additional public information now that you're actually able. That NVIDIA has these things called a streaming cache, meaning that you can miss on the cache as much as you like. And the way that that's implemented in the simulator is that we just give the cache a very large number of MSHRs such that it can saturate memory bandwidth with just 1 or 2 SMs being active. So that's implemented in the simulator, and so you will see code for MSHRs inside the cache implementation. Atomics are another thing that are supported in GPUs. You can do atomics either on the shared scratchpad space or on the global memory space. And atomics are basically read, modify, write operations, and atomic add is a simple example of this. They're coalesced in essentially the same way as normal global memory. So if you have one thread accessing one, trying to do an atomic on one float, atomic add one float in memory, and the adjacent thread attempted to do an atomic add on an adjacent float in memory, it will coalesce those into a single memory access. The exception is when you have different threads trying to do atomics on the same address. And so what happens in the simulator is that it will actually serialize those accesses. And the reason for that is that the addition itself, the atomic operation itself, is not done in the L1, it's done in the L2. So we have to generate a separate transaction for every update to every to a particular float. So if you have all 32 threads in the warp attempting to do an atomic update on a single float value, you will send 32 separate transactions to the L2. That's how it's implemented in the simulator. It's most likely not how it actually works in real hardware. There's ongoing work on trying to fix this and make it act more like what real hardware does. But if you're using the simulator as it is today, that's how the atomics work. The simulator also supports multiple warp schedulers. And so here we're just showing an example of a 2 warp scheduler system where this is similar to the Fermi architecture, where you've got one scheduler that's basically handling all the odd warps and one scheduler handling all the even warps. So they're statically partitioned when the CTA is assigned to the core. Half of the warps in the CTA will go to the odd scheduler, half of the warps will go to the even scheduler. And one thing to note here is that you need to make sure you have enough bandwidth out of your front end to be able to satisfy multiple warp schedulers. So when you do have more than one warp scheduler, the number of fetches that you can do in each cycle needs to also be incremented, which happens inside the simulator. Now, at the very edge of the memory system is the interconnect. So after you've gone through either your load store unit, which is what we were just talking about, or the instruction cache, and you have a miss, you need to satisfy that miss from memory somehow, you will go into the interconnect. And in the simulator, we actually model what's known as a concentration on each of the interconnect ports. So in real machines, you don't want to have a lot of ports on the interconnection network itself because that makes it more expensive and potentially slower. So you want to limit the number of ports on each on this sort of big interconnect that connects all the cores to all the memory partitions. And you can do that by essentially concentrating a set of SIMT cores or a set of SMs to use one particular port in the interconnect. And that's what the simulator does. And there's configuration parameters that you can set to basically say what the level of this concentration is. So the way this works is that this injection port will arbitrate between the SIMT cores. In this case, I'm showing 3 different SIMT cores that are connected to the interconnection port. And then when results come back across the interconnect, they will go into a FIFO that will then get distributed to its respective SIMT core. So let's talk a little bit about this interconnection network. We've talked about the SIMT cores. Now let's talk about the interconnect. So the simulator actually models several different clock domains. So the core clock, or the SIMT core clock, is one clock domain. There's a separate clock for the interconnection network, a separate clock for your L2 cache, and then a separate clock for the DRAM. And the DRAM clock is modeled after what real DRAM clocks are. We basically take the timing parameters from GDDR5 or from HBM, and we instrument the DRAM to be clocked in that way, and that is all modeled inside the simulator. One thing you need to know is that when you cross clock domains, you need to have some type of buffering. This is true in real systems. It's also true in our simulator. The reason is that if you have two different clock domains, you could fill and spill at different rates, and you need something to essentially accommodate the fact that the rates are not always equal. So for example, if you're thinking about the interface between the interconnect and the memory partition, we'll have a buffer in there. That buffer is going to be filled at the rate of the interconnect, and it's going to be drained at the rate of the DRAM. So the DRAM will be taking values off of that at the rate that it's being clocked, which may be different. GPGPU-Sim contains a very detailed interconnection model. It uses this thing called BookSim. It used to be called InterSim, which is an interconnection simulator from Bill Daly's group at Stanford University. And you could do a bunch of different stuff with this simulator. You can set up different topologies, different routing algorithms, change the way the flow control works. All of this are sort of more advanced networking topics that we don't really cover in this class. You'll probably touch on them a little bit in 666 if you're taking it. You don't need to know much about the interconnect if you don't care about it, but it is there if you want to make more detailed changes. Another thing I'll note is that to easily prevent deadlocks in the system, we simulate two separate networks, one network that goes from the SIMT cores out to the memory partitions, and then a separate reply network that goes from the memory partitions back to the SIMT cores. And we do this because it makes it a lot easier to ensure that the interconnect is deadlock free. Here's some examples of topologies you can set up by configuring BookSim. So this is a standard crossbar, which is what the default models and what real machines actually do as far as we can tell, which is basically an all-to-all connective network. You could arrange it as a mesh, meaning you've got sort of cores connected together with sort of individual connections, and you've got the memory controllers spread throughout the mesh in whatever way that you see fit. So you could look at some interesting routing and flow control type problems if your on-chip network looks like this, or you could configure it as a ring network where basically you're only connected to a peer and then it has to ring around. If you're not really worrying too much about the interconnect and it's not part of your project to study it, then this is the interconnect that's going to be set up in the simulator by default, just a simple crossbar. And so here are the interfaces just in pictorial form. Okay, so we've basically got the BookSim is basically a collection of routers. So the router is the interface to the interconnect, and there's going to be a buffer here that is going to sit between the two clock boundaries. So the interconnect is clocked at one particular rate, and the core is clocked at another. The core will be generating, if you're missing in your cache every cycle, then you'll have one cache miss generated per cycle. And then the interconnect will be taking requests from that buffer at a rate of one, what's known as a flit per cycle. What is a flit? Well, the interconnect width may not be the same width as the packets generated by the SIMT core. So for example, the message that says I need this particular address may be 4 bytes, but maybe there's only 16 wires inside the interconnect that can be transferred in one cycle of the router. So you would basically have to take 4 cycles to clear one packet. Okay, so there are some configuration options in terms of how big your flit size is, how big your packet is, what your clocks are, but do sort of know that there is this buffer here that's trying to basically bridge the gap between different clock domains and different sizes of information. And the same is true of the memory partition when it replies with a particular access. So, if it comes back and it says that I've got your 128 bytes, it may take several cycles of the interconnect to actually send that 128 bytes back to the core. Same thing with the L2 cache if you've got the L2 turned on, which it is by default, and all modern machines do have L2s today. That's all I'm really going to say about the interconnection network. The model is very detailed. If you have additional questions, feel free to ask. There hasn't been a lot of work on GPU interconnection networks. There's been a few papers, but not a lot, mostly because real machines just use a relatively simple network, and they essentially over-provision this crossbar such that it's not a bottleneck. But it's modeled in some detail in the simulator if you've got a clever idea or want to try something out. So we'll move on to the last part of the system that's modeled, which is these memory partitions and the GDDR memory itself. So listed here is GDDR3.5. We also model HBM, which is the default in the Titan V configurations that you guys have in the default config that I'm pointing you to in this tutorial. We talked about memory address mapping. So, we went through in some detail how you can select bits from the physical address to determine which channel you go to. So in this picture, each of these memory partitions is a separate memory channel, okay? And the way that the simulator strides the memory across these partitions is very simplistic. So it basically just takes consecutive bytes of consecutive 256 byte regions and then sprays them across all of the partitions in that very straightforward way. You can configure this, and we actually have some options in the simulator to configure it and do some clever hashing, which will help with pathological strides. But by default, I believe that it's still going to do this basic 256 byte interleaving. So just to make it crystal clear what that means, so here's your linear memory space, and we're showing here chunks of 256 bytes. And so the first 256 bytes are going to live inside memory partition 0, the next 256 in memory partition 1, and so on. And so if you're accessing data in a nice strided manner, in a nice linear way, like you're reading, all of your cores are reading this huge chunk of data, which if you think about the way a simple matrix multiplier or vector add works, this will probably be the case, then you'll be having concurrent transactions to all of these memory partitions at the same time. And that's the way that you saturate the memory bandwidth in the system. What's inside these memory partitions? So, to understand what's inside, you have to realize what they need to do. So they live on the other side of the interconnect. So on this side of the interconnect is your core, and then over here you'll have a collection of these partitions. Inside these partitions is one bank of your L2 cache. So if you have, 8 megabytes of L2 cache and 8 memory partitions, then each partition will have 1 megabyte of that L2 cache inside of it. Now, inside this thing, there's a collection of queues that basically buffer between the various components. So you'll have a buffer between the interconnect and the L2. If you have example, a load instruction, you'll query the L2. If it's a hit in the L2, you'll just reply to another buffer and then eventually go back to the interconnection network. If you miss in the L2, there's another queue that the request will go into. Then there's another queue to model some additional latency that exists before we get to go to the DRAM. And then after it goes through that overhead, the initial latency overhead, there is a DRAM access scheduler, which could be used to do out of order memory accesses to try to maximize row buffer locality. And the scheduler will decide what accesses go to DRAM next, which will go to the software timing model for the DRAM that's inside the simulator. It'll figure out how long it's supposed to take before the thing replies. It'll come back to the scheduler, get put into a queue, fill the L2 cache, get put into the next queue to go back to the interconnect, and then eventually go back to the cores. Two things to note in here outside of the normal load store pipeline are this atomic operation unit. So we assume that all of the atomics take place here at the memory partition. So if you do an atomic add, this is where it's assumed to be happening. The other thing that's strange inside this model is this thing called the ROP, which stands for the Raster Operations Pipeline. This is something that's specific to graphics. It's used when you're trying to actually rasterize the screen to figure out what the right pixels are on the screen in any particular frame. And it is historically all of the accesses that have gone to this memory partition have gone through this ROP pipeline, even if they weren't doing any raster operations. In GPGPU-Sim, you are able to bypass the ROP queue. It essentially doesn't really do anything except add some additional delay. And so in the early GPUs where all of the accesses went through the ROP queue, it was important to model that additional delay to go to the L2 cache. In modern machines, it's probably less important as this is likely bypassed. But that's what those units are. And essentially what this is, if you're curious, is like a little processor in memory. It attempts to do known operations that are common in graphics at the L2 level, so that way you don't have to go back to the core to essentially rasterize pixels on the screen because it's such a common operation in GPUs. But for the purposes of CUDA, general purpose programs, it doesn't really have a use other than sort of being in the way. How is the L2 arranged? This cache will cache all memory, local memory, global memory, and structured memory, etc. The way that it operates for both local and global memory is identical. So it is write back for both, and it is write allocate for both. One thing to note about the L2 cache is that the memory copy engine will also go through the L2. So when you do a CUDA mem copy from the CPU over to the GPU, all of those will go through the L2, meaning that if you have a mem copy that fits in the L2, then you will never miss in the L2 when you try to read from it. You won't even have any cold start misses when you start up the GPU. And the same is true when you're reading back. So essentially, you always have to go through the L2 before you go to the DRAM, even when you're doing things from the mem copy engine. And obviously, if you miss in this L2, then you go through to your DRAM. So one way to model DRAM is just with a fixed constant latency. So you say that, I'm always going to assume that it's going to be 200 cycles to go to DRAM if I miss in my L2 cache, which is probably a fair approximation, but it's not always true, especially in GPUs. So this little plot just shows an example of, if we model the DRAM, model row buffers in some level of detail, what is the average memory access latency for a collection of different applications? And you can see that it varies widely. So just simply saying that it's going to take the same amount of time to access DRAM regardless of any of these characteristics like bank level parallelism, row buffer locality, etc., is missing some of the detail that you need to really model these benchmarks well. And so inside the simulator, we actually do have a DRAM model that models basically the same thing that we talked about in class, right? So this is again is a repeat of what we've talked about in class, where you've got basically this row buffer. You read values out of the array from the row buffer, and then when you're done reading, you actually have to pre-charge the data back into the array, and all these things take time. So when you switch from one row to the next, there is a huge cost associated with that, and that is modeled inside the simulator, inside the dram.cc file. Now, why is this important? Well, it means that you can actually play games with the memory controller to do more intelligent memory timing. So the simulator comes with two different pre-built types of memory controllers. A simple FIFO, oops, I'm sorry, let me just go back. A simple FIFO memory controller, which just processes the accesses in the order that they came, and then a first ready, first come, first serve scheduling algorithm, which will process those requests out of order. Obviously, from 565 that if you want to do something out of order, you're going to need some type of associative search to figure out which ones are going to need to be accessed next, similar to the way that the out of order engines work in contemporary CPU cores. So to give you a little example of why this matters, let's say we had two cores. One core is having two requests to row A, another core is having two requests to row B. They show up at the interconnect at roughly the same time. If the interconnect is doing a round robin arbitration, then you're going to pick the request from this core first, then pick the request from this core next. And what's going to happen is you pick this request, it'll transfer over to the DRAM, and it'll end up in the DRAM memory controller. You'll do the next request, it'll end up in the DRAM memory controller. The next request from here, the next request from here, and so on. And then what you end up with is this ping-ponging effect between row A and row B in the requests seen by the DRAM controller. Now, if you have just a simple FIFO scheduler, you're going to have something like this, where you access row A, then you're going to have to switch the rows, so you miss in the row buffer, and that has, overheads associated with it. And then you access row B, then you have to switch again to go back to row A, and then you essentially ping pong between the two, and it vastly affects your memory access latency. But if you have a first ready, first come, first serve out of order DRAM access scheduler, then you can do an associative search in this queue, and you can pick out all of the elements that are accessing the same row, and then do those contiguously so that there's only one row switch here, and it vastly decreases the amount of time wasted, getting these requests back from memory. And that is all modeled in the simulator, and you can go ahead and implement any advanced type of out of order scheduler that you'd like inside the simulator, and you should be able to see different results. And you can just flip a switch in the configuration file to see what the difference between the FIFO and the first ready, first come, first serve scheduler is, by default. So that's it for this first segment of the GPGPU-Sim tutorial. So none of this was any code overview. It's just giving you a sense of what is modeled in the system. And to sort of recap, what's modeled is basically everything that's in this picture at a fairly low level of detail. DRAM is modeled with various timing parameters. The memory partitions are modeled with various queues. The interconnect is modeled using the BookSim simulator, and then the core model is essentially meant to mirror the things that we've talked about in class, all the way from the 3 different types of schedulers, the operand collectors, to the multiple warp schedulers, etc. And all of that is modeled in the timing model for GPGPU-Sim. So I'm going to end this first segment now, and then the next segment will focus more on the software architecture and how the code is designed, where stuff is, and give you some insight into how you can make some changes to actually model something inside the simulator. Okay, thank you.